I am Assistant Professor Urmi Shah from ICT Department of LG Institute of Engineering and Technology. In this session, we will be moving ahead with the second unit of our Telecommunication Engineering course, that is Digital Circuit Switching Network. So this is the second unit of our syllabus and we will be moving ahead with the further topics in this unit. In the previous session, we discussed about the circuit switching network, what is a switching network, what are the probabilities of blocking a network, and how you can avoid the blocking of network. In this session, we will be continuing with the two-stage, three-stage networks, and this is session number 12 of our Telecommunication Engineering course. So let's move ahead with the second unit of our subject. So what are the topics that we are going to cover in this session? So firstly, we will be looking forward with a two-stage network. What is three-stage network? What are the end stages of network? What are non-blocking switches? What is a two-blocking network? And what is a blocking probability? So these are the topics that we are going to cover in this session. Basically, in the previous session, I discussed about a two-stage network. Basically, you can see over here. So basically, the first topic of our session is two-stage representation of N cross N network. Basically, as you can see over here, this is a diagram of two-stage representation of N cross N network. So as you can see over here, at the input side, you have N inlet, that is N number of inputs, and also at the output side, as you can see over here, you have N outputs. So basically, your matrices which is created at the input side is of N cross K, and at the output side, it is the reverse of whatever it was there on the input side, because whatever number of inputs you are applying at the input side must be equally retrieved back at the output side. So exactly opposite of that network will give us K cross N network. So finally at the output side we will have N number of outlets. For any single stage network, there exists an equivalent multi-stage network. So this is a complete multi-stage network which is kept inside a single stage network. Nextly, basically, if you have N cross N network and instead of N I am keeping 2, then it will become my two-stage network or 2 cross 2 network, where I will have 2 inputs and 2 outputs. So this way, by keeping or assuming the value of N, we can create any N cross N network. So, N cross N single stage network with capacity K can be realized by a two-stage network of N cross K and K cross N. Now while here the terminology stage has come, that how you can interpret that it is a two-stage network. So firstly, over here you have two blocks via which your input is going towards the output side. If you have a single media, single controller section, directly input given to that controller and output generated from that controller section, then it will be a single stage network. But as you can see in the diagram, your N number of inlet or N input are going to first N cross K network, then it is going to K cross N network, and finally it is generating the N outlet. So that's why this is a two-stage network. After passing from first stage, your input is going as an input to K cross N network. So it is having a filtering process of 2 stages, and after that the final output is produced. So that's why This is termed as a two-stage representation of N cross N network, where keep one thing in mind that N are the number of inputs and output. And what is K? K represents the stages. If you have two stage, then your input and output will have in between two stages before the generation of output coming from input. So nextly, let's understand what are the different representation, and yes, how you will be connecting your inputs and your stage network elements. So any of the N inlet can be connected to any of the K outputs of first stage. So whatever number of inputs you have on the input side, any of that input you can connect to any of the output of the K block of the first stage. So this is the connection which is created according to the feasibility. Similarly, any of the K inputs can be connected to any of the N outputs of second stage. After first stage, you can have connection of N inlet with any of the K output, and similarly for second stage, any number of K input can connect with N number of output. So this is how the connections of switching element will be provided via this stage network representation. Nextly, there are K alternative paths and two NK switching elements. So basically, you will have a K alternative path and total number of switching elements for all the blocks will be equal to 2NK, and represents whatever the number of inlet and outlet are, and K will represent the output generated after first and second stage, between first and second stage. Nextly, what are the switching elements in switching network? So basically, in any stage or in each stage, you will require NK switching elements. If you are having two stages, then you will require two NK switching elements. But every stage, you require NK switching elements. Assume only a fraction of subscriber to be active on an average K that is equal to N by 16. Let's now understand this switching element concept by understanding an example. So let's assume that you have a fraction of subscriber which are active for an average K values, that is N by 16. N by 16 subscribers are active at that time. So number of switching elements, that is S is equal to 2NK. So after assuming the value 2N, instead of K you will assume N by 16. So your answer will be, what will be your answer? It will be N by 4 elements. N by 4 elements will be there. And if you have N is equal to 1024, then this many subscribers will be active at that time. This many switching elements will be involved in the switching network at that time. So this way you can calculate the switching capacity, and the switching matrix is given to you, then you can practically realize the switching network. But again, the limitation over here is if you have a large value of N. For a large value of N, the switching network or the switching matrix N cross K may still be difficult to realize practically. Why it is difficult to realize practically? Because more number of switching elements, the more connections you have to make up with the subscribers. So that will be an issue in this large switching element. So that is the drawback. Otherwise, you can practically realize this type of network. So this is a two-stage network with multiple switching matrices. Over here, there are M inlets. In the figure, you can see over here, there are M inlets. And total there are N outlets. Now, M inlets are divided here into R number of blocks. You can see over here, the inlet side, the blocks are 1, 2, up to R. So, M inlets are divided into R blocks of P inlet. Total the input which are going, those are in P form. So M is equal to PR. P is the inlet element and total it is divided in R number of sections. So P into R will be your number of inlet. Same way, now at the output side, you can see over here that total N outlets are there. N outlets are divided over here into S blocks. From 1 to S blocks are the number of blocks which are associated on your output matrice or output switching network. So, N outlets are divided into S blocks of Q outlet. The output which is coming, that is in form of Q. So Q outlet is there. So your N will be equal to Q into S. N is your number of outlets. So it is a product of Q into S. S is the number of blocks and Q is the coming outlet. So this way you can analyze the number of inputs and number of outputs by analyzing the whole network, which is comprising of multiple switching matrices. So this way the whole switching network is designed. Now the network parameter says that for full connectivity there must be at least one outlet from each block in the first stage, that is terminating as an inlet on every block of second stage. So block sizes are P multiplied by S and R multiplied by Q. So that is the block size. P was the number of inlet at the input side. S is the number of stages or number of blocks on outlet side. R is the number of blocks on input side and Q is the coming outlet. So your S, that is the switching capacity, can be denoted as PSR plus QRS, where P is the number of inputs that are going. Then S is the outlet side blocks, R is this number of stages in input, Q is the coming outlet, R are the number of input stages on inlet side, S is the number of outlet stages. So putting the values of M and N, here your switching capacity can be denoted as MS plus NR. So the number of simultaneous calls in a network having switching capacity R into S. So this is the simple formula. So this formula you can have for the analysis of any switching network. Now coming to the important topic, that is blocking network. What is basically a blocking network? For RS connections to be simultaneously active, the S active inputs in one block of the stage must be uniformly distributed across all the S blocks in the second stage at the rate of 1 per block. Blocking may occur in two conditions. Calls are uniformly distributed. There are RS calls in progress and RS plus 1th call will arrive. If calls are not uniformly distributed, there is a call in progress from the first block, from the first stage, and there will be a call from the jth block in the second stage. Another call originates in the ith block destined to the jth block. So these conditions will create a blocking network. No call will be entertained by the inlet towards the output side. So these are the conditions for blocking of network. You must have the calling structure equally divided in the two stages. If the channel capacity or the switching capacity is equal to RS, then RS connections must be simultaneously active for both the stages of your switching network and it must be uniformly distributed. So these are the criteria and these are the conditions for avoiding a blocking network. Nextly, coming to the blocking network, let's understand what are the blocking probability for a blocking network. So this is an important formula which can be asked in your examination, that derive the blocking probability formula where the network can be blocked. So let's understand this. Let alpha be the probability that a given inlet is active. Now, probability when an outlet at the ith block is active is beta. So these are the two assumptions which before deriving the probability we are assuming. Beta over here is equal to P multiplied by alpha divided by S. The probability that another inlet becomes active and seeks an outlet other than the one which already is given by is equal to P minus 1 into alpha divided by S minus 1. So one inlet will be lesser, that's why from the above formula we have subtracted value 1. Now probability that an ready active outlet is sought, that is PV is equal to P alpha divided by S into 1 minus P minus 1 alpha divided by S minus 1. So this is the overall blocking probability that a network will be blocked if this criteria or if this condition arises. Substituting over here the value of P, that is equal to M by R, we will have the formula for probability of blocking network as M multiplied by alpha divided by RS into 1 minus M divided by R minus 1 into alpha divided by S minus 1. So what actually happened over here? We have just substituted the value of P is equal to M by R in the above equation, and then we concluded with the formulae for the blocking probability of this particular network. So this way we can have the derivation of blocking network and what is the probability that a network will be blocked. If in this equation or if in the previous equation, if we are reducing the value of S and R, then S can be minimized, but if we decrease S and R, then we are increasing the blocking probability. So we have to choose values for S and R as small as possible, but giving sufficient links to provide a reasonable grade of service. So these are the criteria for providing or for avoiding the blocking of any switching network. Now, nextly, this is a three-stage network. Basically, what we saw in the previous slide was a two-stage network. Moving ahead, we have another kind of network, that is a three-stage network. In a three-stage network, as you can see over here, you will have n number of inputs or n number of inlets, and that will be applied to a three different stages. So here you can see that total first stage is there, which is having n cross m matrix. You can see in the above section. Then for the second stage you have R cross R switching matrix, and in the third stage you can see you have M cross N matrix. So this way at all the different levels of stages, different switching matrices and switching capacities will be allocated for at a time having active network. So this way we can have n number of inlets at the input side for a three-stage network, and total n in outlet is coming from all the blocks at the output of third stage. So this way we can have a three-stage network. Coming to the next network, this is n-stage network. In n-stage, we can have n number of stages. In the two-stage network, we had two stages before inlet and outlet. Now, between inlet and outlet, you can have n number of stages, and here you cannot have a proper switching matrices because it will be in terms of n stages. So, this network can be described in form of such matrices switching network that will have n1 inlet and n2 outlet, having at first stage n1 cross m matrix, in the second stage R1 cross R2 matrix, and in the final stage M cross N2 matrix. Now this will depend on the value of N1, N2, M, R1 and R2. So these are the switching elements value on which the designing of N stage network will depend. Moving ahead, this is a two-stage network with multiple switching matrices which we have discussed before. It is having comprising of M inlets and N outlets. This we have already discussed. Nextly, we were discussing about blocking network, but this formally and what is a blocking network, that we have already derived. Now based on this, now we will be understanding what are inlets and outlets. So M inlet versus N outlet. Basically, if N is greater than M, network is expanding traffic, and if M is greater than N, then it is concentrating the traffic. These things we will be able to understand when we will be learning about the third unit of our Telecommunication Engineering subject, which is related to traffic engineering. So if N is greater than M, then your network will be having an expanded traffic. But if your network has inlet greater than the number of outlets, then it will be concentrating the traffic. If N is equal to M, then matrix size will be uniform. That is, R will be equal to S and P will be equal to Q. So that is a uniform stage. To avoid a blocking of network, you should follow N is equal to M. That is, number of inlet should be equal to number of outlet. So these are the criteria for avoiding traffic. Nextly, let's understand this via one problem. In the two-stage network discussed so far, there is only one link between a block in the first stage and a block in the second stage. What will happen if this particular link fails? Risk of severe blocking will arise in this network, and how we can improve the performance. So this is your task, that how you will avoid the traffic or the blocking of network based on the previous conditions which we have discussed, or based on the blocking probability criteria. So this is the question given to you. So basically in this stage, if there is only one link between a block in the first stage and the second stage, how we will avoid the blocking of network. So the solution for this problem is, we can increase the number of links between the blocks of the stages, or we can consider k links being introduced between every first and second stage pair. So this is the solution for our problem. Either you can increase the number of links between the block of stages, or you can introduce k links between first and second stage pair. So this is the solution for this particular problem. Now, basically, what is a non-blocking network? Up till now, we were studying about what is a blocking network and why we are using it. But let's now understand what is a non-blocking network. In order to make the network non-blocking, you must have the fulfillment of following criteria, which include k is equal to root of n, for m is equal to n, p is equal to q is equal to root of n, and r is equal to s is equal to k root of n. So So these are the criteria if you want to have uniform distribution of the network. So now S is equal to Ms plus Nr, which will be equal to 2Nr, that is 2N square. And Sc is equal to Rs is equal to root n into root n, so it will give us n. So a two-stage non-blocking network requires twice the number of switching elements as the single-stage non-blocking network. So this is a very important criteria. You must mark it or highlight it. If a two-stage non-blocking network requires twice the number of switching elements as the single non-blocking network. So compared to a single stage non-blocking network, you will require the double switching elements in two-stage network. Following are the references for the topics that we have covered today. In the upcoming sessions, we will be continuing with our digital circuit switching network. You can refer these books for the topics that we have covered today. Thank you very much for watching this session. Thank you.